All right, we'll get started. So this is data models and consumer idioms using Apache Kafka. My name is Erik Onnen. I'm the director of architecture at UrbanAirship. That basically means that I spend my time making sure that we deliver scalable systems that meet the SLAs for our customers, that we don't go down, and that we have good throughput. I still luckily get to write a decent amount of code in the process. Formerly, I've worked at a couple of companies that are up there on the board. I spend most of my time in Java, C++, and Python when I'm not doing hand-wavy things. I do have a background in messaging systems, so I have contributed code to ActiveMQ. I've worked on several global TIBCO deployments across multiple continents, and worked for commercial ESB vendors as well. So Kafka is something that is relatively near and dear to my heart in terms of how we move around data in an asynchronous format. So UrbanAirship, just real briefly, is a company that specializes as an engagement platform using location and push notifications. A sample of this would be we have a representation of our segments product that's up on the screen on the right-hand side. And what that would let you do would be if you wanted to target all users in the city of San Francisco or people who had been to San Francisco in the last month and send them a message specifically for fans of Jay-Z and Beyonce because there's a concert coming up. Our infrastructure is built to scale to large numbers of platforms and large numbers of devices. And at any given point in time right now, we can accomplish this functionality for getting close to over 500 million devices. Analytics and delivery are pretty critical to what we do. When we send a message, we want to know if it's received well and what we sort of have multiple metrics for. Is it a hard conversion after we deliver a message, but also how does it influence application behavior after the message arrives? And we have high precision targeting capabilities which allow us to get these messages to exactly the right people when our customers want us to get them there. So I mention all of this because for each of these capabilities, Kafka is a fundamental underpinning for us. This isn't really my product pitch. This is to say that Kafka is a critical component to how we do pretty much the majority of our business today. So I'm going to go in a little bit more depth in terms of how we use Kafka at UrbanAirship up front. I'm going to give a brief, well, maybe slightly longer than brief, architectural digest of Kafka with an attempt to not repeat anything that is easily obtainable on the website. This is really going to be a dive into the critical things that you won't get from reading quickly through the website that you learn after you've been using Kafka for, say, a year. Then we'll move into data structures and stream processing. So now that we understand the fundamentals of how Kafka works, what limitations it poses on actual consumers of messages, how do you structure those consumers, what are different ways that you can take that data and get it into, say, a durable storage system. And then this being Surge, the last third of the talk or so should focus on the Kafka operational disaster porn, and there's a good healthy dose of that too. So this is a quote from the Kafka website that sort of describes at a high level what Kafka does. The thing I wanted to call out here was people often think of Kafka as being a peer to scribe, which is commonly thought of as a way to move around log files and do log aggregation across a large number of hosts. We do not actually view Kafka that way. It's perfectly fine for that. But we actually view Kafka as a more fundamental underpinning for how do we do asynchronous messaging that doesn't require low levels of latency through our systems. So Kafka's on the critical path for many of our core capabilities. Device metadata. So if you have an application on an iPhone that uses our service, every time that application is foregrounded, we send metadata about the application up to our servers. That comes in through an HTTP ingress point and ultimately through Kafka until it's stored in a durable storage engine. We use it for message delivery analytics. So every time we deliver a message, between the time that an API call comes into our system to the time that results in a message being delivered to the time that we see a user interact with that message, that's 3 data points that we put into Kafka. Device connectivity state. Right now we have well north of 10 million persistent socket connections into our infrastructure that are all mobile devices. Every time a device connects or disconnects to that infrastructure for the purpose of receiving push, we fire a Kafka event. There's an unbelievable amount of thrash in terms of how often mobile devices lose their connectivity. So there's a really high rate of messages coming through there. Kafka also feeds our operational data warehouse. So what that means is when we have an RPC call into our internal infrastructure to say look up the location of a device or to load the device metadata, that RPC call, the metrics around it, are operational data points that we want to save. And so we feed those into our operational data warehouse. That is also done through Kafka. So we currently run 3 Kafka clusters. In aggregate, they do over 7 billion messages a day. At peak capacity, we've observed a single consumer able to handle 750,000 messages. I should mention that that was in the event of a network split, where that consumer was, and 1/3 of the Kafka cluster were effectively partitioned from the rest of the network, and it got no data. When it came back online, the consumer was actually able to consume at about 750,000 messages a second. That was sustained for over 30 seconds, and then by that time, it had actually caught up to the message volume. That consumer was doing a read-write CAS operation on a database. So we were able to move a lot of data. It was the consumer itself, the operation was clearly the bottleneck. Kafka probably could have gone much faster. Everything we do is on bare metal in a hosted MSP. We had a long history of emerging out of EC2 to our own data center, and there's plenty of talks out there on that saga if that's a topic that's interesting to you. Kafka's factoring prominently into our multi-facility architecture. So we're currently in the Reston, Virginia facility, which is the Equinix facility, same as EC2, for example, and a lot of other people. And as we look to move to multiple facilities, Kafka is going to be a key part of how we bridge the data between those facilities. So at a very high level, this is what a working Kafka cluster looks like. We have producers on the left that are delivering messages into brokers. In the most simple situation possible, messages go from producer to broker and then into a consumer. There's a Zookeeper ensemble at the top, which is effectively optional for the brokers and the producers. The brokers can publish their location to the producers, and the producers can automatically discover new brokers on the fly that way. We don't actually run our Kafka clusters that way in production. That way we don't have to have a Zookeeper library on the client side where the producers live. But ultimately, the brokers deliver messages to the consumers. This would be the most simple possible solution for or possible incarnation of message delivery in a Kafka architecture. In reality, wrong way. In reality, it looks like that, where effectively producers are spanning messages out to multiple brokers, and then any one consumer can consume from one or more of the brokers that are in the cluster. This will become critical later when we look at some of the limitations of Kafka. It's important at this point just to understand that if you're a consumer, you may get messages from one broker or two, or all the brokers that are participating in the Kafka cluster. So the core concepts underpinning Kafka, Kafka is a publish-subscribe system, or pub-sub, if you come from more of a JMS universe. It is definitely not a queue. So effectively, one producer writes a message into Kafka, and then 0 or more consumers may see that. A message may fire into the ether inside of Kafka and never actually emerge back. That's a perfectly valid use case for certain types of data. The core implication there is that if you expect to be able to look at a queue depth and see how many messages are in that queue waiting to be consumed, Kafka doesn't support that type of behavior, at least not easily. Consumers are not contending with each other for the messages. So the act of publishing a message into a topic means that any two consumers in different groups are not contending for that message. They'll both get it. It doesn't really matter how many consumer groups there are in Kafka, up to a pretty reasonable extent in the neighborhood of 50,000 or so. Messages are retained for a configured window of time. So our clusters, we typically run them for 7 days, which means if you bring a new consumer online 5 days after the time you first light up a new Kafka cluster, it has access to all 5 days previous of that data, assuming it can consume the data fast enough. And then messages are grouped by topics. So when you submit a message into the Kafka infrastructure, that goes into a topic, and then consumers read from individual topics. By way of example, if you have a single consumer thread, regardless of the number of brokers you have, that one thread is going to read all messages from a given topic. If we stand up 2 consumer threads, each one is going to get roughly half the messages from that topic. And if we stand up 3 consumers, each one will get approximately 1/3 of the messages. There'll be some drift there, but generally it balances out fairly well. On the producer side, Kafka producers have no idea who's going to consume the messages. It's largely a fire and forget mechanism, even down to the protocol level. So the producers will effectively deliver one message to one topic on one broker. I have an asterisk there. There is replication development that is underway in Kafka, but it's not currently present. So in the sense of replication, a message may actually make it to more than one broker. But in the current incarnation today, a message goes to one and only one broker. That message within the broker and within the topic is delivered to a specific partition. And again, generally this isn't critical for understanding the architecture, but it will play into when we look at how to correctly build consumers of the messages downstream. Messages are not act in any way. So again, it's fire and forget. They're not act when they get into the broker. They're not act when they're on disk. It is literally, if your socket is torn down, you need to start writing messages somewhere else. There are trade-offs that you make in that sense that may not be an acceptable trade-off for you. And we'll go into some of those in a bit. Messages are largely opaque to producers. Producers do have the option of self-selecting which partitions in a topic the message will be delivered to. That is typically an idiom that we do not follow for the sense that right now we get a random distribution across all partitions. And in our world, if we were to partition by, say, an application, we would run the risk of having convergence around specific partitions where load would be too high in one partition and too low in another partition. So we force ourselves to always just have a pure random distribution across all the partitions. It is possible to do. I'm not familiar with a lot of people who actually run Kafka that way. And messages are generally sent at or below a configured size. You'll also note the footnote there. That will come into play later, too. So brokers are dumb by design. They have no shared state. They receive a message. They have a duty to persist that message after certain configurations have elapsed. And then consumers ask the broker for the messages. That's really all the broker does. The brokers do publish small bits of metadata to Zookeeper, but that's generally not relevant for the overall understanding of how the brokers participate in a cluster. Messages are pulled by consumers. This is critical. A broker has no notion of, oh, I still need to send this message to consumer X, Y, or Z. Consumers wake up and they understand where they're at in the overall group and how to pull messages from the broker. So really, all the broker has to do is accept new messages, store them, and send them in a very efficient manner downstream to the consumers. Brokers manage sets of segment files, one per topic and partition combination, which means that in the topic of sports, for partition 1, there's going to be a segment file that is all the messages that have been allocated to that partition. Effectively, those segment files are mapped into memory by Kafka, and then deliveries effectively become send file calls on those mapped files, which makes this a very efficient operation. We avoid a user system user copy, and it's effectively one of the most efficient ways of taking a file and sending it down the wire, which is really all the Kafka broker has to do. So as an example, the brokers, this is taken from one of our 3 clusters, that is our operational data warehouse cluster, sort of our infrastructure event cluster. The brokers have a very lightweight footprint. You can see that SDB1, which is the volume that the data is actually on, is only at about 2.1% utilization, and Zookeeper typically is the leader on top, although in this case Kafka is there. But we're running at a 15-minute load factor of 1. Right? This box is barely working and moving around tens of thousands of messages to probably 40 different discrete consumers somewhere on the network. And they all pretty much look like this host. The Kafka broker takes the position that you should not fear the JVM, but rather put it into a corner and let it do what it's good at doing. By that, most of the heavy lifting is done in the system calls that I mentioned earlier. Right? So send file calls on an mapped file. Very little is actually done in the JVM. The heavy lifting is done by the operating system in the kernel. Kafka does very minimal on-heap buffering. So a message comes in, it's written into the segment files, and then effectively the message is garbage at that point and can be garbage collected. So taking a sample from the host that we had the top and the IO stat output from previously, a 20-minute sample had about 100, or had exactly 100 par new garbage collections, and it was a total time on, excuse me, a total user time of 0.42 seconds. So we're well under 1% of total CPU time in garbage collection in our Kafka brokers. It's pretty much a non-entity in terms of the overhead of the system. Consumers are configured for one and only one group. So a group consumes messages from a topic, and if there's one consumer thread participating in that group, or 30, the messages are divided among those groups. If you want to reconsume a topic, you change the group name, and you start again from the oldest data file that's present. Messages are iterated in a Kafka message stream object, whether it's in Java or Scala. And those iterators never stop, but they may actually block. Right? So you're effectively calling next on this object, and it gives you a message object to process if there's one there. If there's not one there, your consumer thread blocks. A message stream is one of these Kafka message stream objects. Effectively, is composed of a topic, so sports in this case, and then a group, and you may have a group for the sports event log, i.e. a score happened, but one for the updater that actually updates some sort of durable store that then the web application is going to read out. But then brokers are also part of a specific stream, right? So a stream may assemble a message from one or more brokers, and then one or more partitions from each of those brokers. So a stream is really sort of a very high-level abstraction around these lower-level silos of data. So we found Kafka to be excellent for small expressive messages. Bring your own data, though. We say that because effectively every message that we put into Kafka can be operated on by a consumer. Consumer doesn't have to take fields and look them up in other services to be effective with that data. If they did, the latency of those consumers would fall through the floor. They would be way too slow, and they wouldn't actually keep up with the message volume. So we take the burden of packing all the data that we need into protocol buffers upstream before they get into Kafka so that the consumers can act on what they need to without having to consult an external service. Throughput. Kafka effectively, I've worked with a lot of JMS systems, AMQP systems for PubSub, and Kafka decimates all of them. I've not seen anything come close, especially at the high end of 750,000 messages per second. That was across multiple consumers. The system can move data very, very quick. We've seen better than 70% throughput compared to, say, Beanstalk D, which is more of a queuing-based approach. We use both in our architecture, but we're gravitating more and more towards Kafka, where we can live with the concessions. And Kafka scales very well with a number of consumers and topics. So adding new topics and adding more consumers to a topic is effectively a free operation up until people have seen the beginnings of degradations where you have around 50,000 consumer groups. LinkedIn has a lot of really excellent information published on the actual Kafka wiki in terms of where they've seen the upper bounds, but it's fairly high. I can't imagine us ever having, say, more than 1,000 consumer groups on a specific topic. It's not a realistic thing. And thankfully, Kafka consumers rebalance very well in the case of, say, a graceful rolling restart or failure or shutdown. So that means if I have 3 consumers that are consuming from a topic and one of them goes away, all the data that that consumer was consuming is redivided among the other 2 consumers. When a new one comes online, it may rebalance the data. It may take a little bit of time. The algorithm is fairly complicated, and I won't pretend to completely understand how it works. But generally, Kafka does a good job of distributing messages, particularly in the case of failures. Kafka is excellent for rewind and time scenarios. We use this a lot in the case of, say, an operational anomaly, where we know that in the last 2 days, we've seen some erratic behavior, but given our monitoring system, we can't quite stitch everything together. We can, for virtually free, go back in time, stand up a new consumer in a new group, and replay 2 days' worth of operational data, and do different higher-level aggregations to try and sort of look for what's missing. We do this all the time. It's a fairly common occurrence for us. And in Kafka, being a pub subsystem allows fairly transient taps in the stream of data. So if we have a new application launch, and we don't quite understand how's that application behaving, in other words, are we seeing a surge that happens at 8 a.m. Pacific that ebbs by 5 p.m. Pacific? We can tap into these streams of data transparently, not affect the production consumers, but effectively mine other things for data. And we get that for free given the way the architecture works. But all those good things aside, Kafka makes some critical concessions. On the broker side, data is not redundant. So if a broker dies, you have to restore that broker to get back at its data. If we have a power failure on a broker machine, we can still recover the disks, we can still get at the data, but if you lose the hard drives, for example, on a particular host, you're not going to get that data back for anybody who hasn't already seen it. There are, of course, ways to get around that, right? So we have redundant mirrored volumes, we have redundant hardware in terms of power supply, in terms of controllers, but you can also consume really quickly, right? If you're close to the bleeding edge and that broker goes down, you lose a very small window of data. In most cases where we use Kafka, that's an acceptable risk, but it may not be for all use cases for sure. I have had discussions with people talking about persisting journals or segment files to shared storage using BRDB. I feel like at that point, if you really care about the redundancy of your data, then Kafka is probably not the right solution for you. It would theoretically work fine, assuming you could get the network I/O that you needed out of the storage volumes, but that's not something that we've really considered doing. And replication is on the roadmap. So replication will, again, sort of narrow that window where there's potential data loss, but I still think it won't fully solve that problem. So segment corruption on a broker can be fatal for an entire topic and partition. It's localized to a partition. So for example, on each one of our brokers, we run 32 partitions. If we lose a segment file, we lose 1/32 of the data on that one broker. It's possible. The segment file format is fairly pliable, so we have, on occasion, pruned specific corrupt entries out of a segment file using hex editors. But then we're manipulating Zookeeper, and it's a really tedious process. More often than not, for, say, the operational store, if we can afford to lose the data, we just delete the entire segment file and move on. And you can configure the size of segment files so that you're going to get narrow that window of potential data loss. On the consumer side, there are several concessions as well. Most importantly, well, there's really 2 critical takeaways here. One is that messages can be delivered out of order. So this is a sample of 2 message streams. We have producer 1 producing messages P10 through P13, and producer 2 delivering messages P20 through P23. From the producer side, these appear as sequential events. So consider the times to be roughly aligned with the IDs. The producers can theoretically, however, tear those streams across 2 different brokers. And then a consumer can likewise read different pieces of those streams back in different order. So it's perfectly possible, and does happen, although not that frequently, for a given consumer to actually see the same event stream as the producer wrote it completely out of order. That may or may not be a problem, depending on what you're doing with your data. And that's where we sort of get into the message idioms later. There is no such thing as once and only once semantics. If you come from a messaging background, this is usually a pretty big thing in, say, the JMS world, where there's a very heavy belief that you deliver a message and you must act that message. And once it's act, it cannot possibly be delivered to somebody else. Kafka makes no claims that it will not deliver messages multiple times, which effectively puts a burden on the consumers. Consumers have to be able to handle the same message multiple times. If they can't, you will eventually get data corruption. There are a lot of different ways that a message can be replayed. It's not steady operating state, but it does happen. A rebalance of consumers after a hard fail can result in redelivery. So that has happened to us. If a consumer is shut down uncleanly, if somebody kill -9s a consumer for no good reason, or if it's unable to actually write its offset back in a zookeeper, then when somebody else claims that offset, when a different consumer claims that offset, they're going to potentially see some of the same data that was delivered to that consumer. So effectively, the key TLDR here, I think, is the possibility of out of order and redelivery required that if you are dealing with systems of record, you have to be capable of supporting idempotent and commutative consumers. And so we're going to go into that now. So I mentioned we use Kafka for analytics. In the analytics case, our producers write data to Kafka, and the consumers create dimensional indexes in HBase. And the burden that I mentioned earlier effectively means that as we go to rewrite an index entry, we need to make sure that if that entry is already in place, that it becomes an idempotent operation, and we handle that appropriately. Likewise, if there's an entry in place that effectively represents a deletion, we have to make sure to not overwrite that. In other words, a deletion and an update have to be commutative. Operational data, our producers are writing service data to Kafka. So we're delivering a message from a delivery tier service that's talking to Apple's push notification service, for example. A message is emitted into Kafka, and the consumers are writing to an operational data warehouse, which right now is HBase as JSON, but that'll probably change in the near future to OpenTSDB, for example. We also have presence data, where consumers are, when a device connects to our edge tier delivery infrastructure, we emit an event that says this device is connected here. And then those consumers actually write that data into LevelDB. But the most interesting case, I think, for the purposes of this talk, is going to be how we handle this sort of idempotent commutative merge with our device metadata. So the canonical example that we use in demos and for sales pitches, et cetera, is that the BET app uses our software. And in the BET app, you can favorite different artists. So you can go into I can open my BET app, and I can say, I would like to favorite Jay-Z, and I would like to favorite Beyonce, and then I would like to favorite Nickelback. Oh, wait, I'm probably not a fan of Nickelback and Jay-Z and Beyonce, so I'm going to unwind that. From a data perspective, when you're interacting with the device, this is what we see. So first we see, okay, the device is ponies, and it's setting tags Beyonce. A tag is an opaque named field for us that has, or sorry, the field name is not opaque, but the value is opaque. We don't really know what it means. So we've got a tag of Beyonce. We have a timestamp of 1. That would really be an epic millisecond timestamp, but just for simplicity's sake, we'll number these sequentially. Then we get another update when the user favorites, oh, I also want to favorite Jay-Z and Nickelback. But that's a problem. The user doesn't actually want to favorite Nickelback, so they're turning off Nickelback. So the last update we see is the tag should be Beyonce, Jay-Z, and not Nickelback, and a timestamp of 3. So the first primitive incarnation of how we would store this data, and I should really discuss what we end up doing with this, is that tag data allows some of the specific targeting that we talked about earlier, right? So I want to be able to send a message to fans of Jay-Z and Beyonce, but not Nickelback. We store all that data, and then if you saw my colleague Pancake's talk yesterday, he sort of went into how we actually index that and look it all up and then deliver messages to it. So what we're talking about here is all those tags are coming in, how are we actually storing that in a tag indexing system? So the most primitive incarnation here would be blast a row into a data storage system, whether it's, I'm going to actually cover RDBMS and column stores, not to use the word, I refuse to use the word NoSQL, so I'll use column store in this case. But in an RDBMS, the most primitive incarnation here would be insert or update the device metadata table with the device ID, so ponies, and then a blob of what the tags are. We're denormalizing here. We're not going to write a tags table. There's no way we're going to be able to join when we need to. It's going to be way too expensive at the scale that we deal with. And in the column store, we write the key as a device ID. We're going to leave our column empty because we don't really care about it. We're just trying to retrieve the blob. The blob, again, is the set of tags. In both cases, these are idempotent. I can rewrite the same values as many times as I want, and they'll either no-op or write over what's already in place, depending on the underlying implementation of the storage engine. But this is a pretty large fail, because, again, mutations can arrive out of order, and so if we're just blowing away the most recent entry, we're going to actually have corrupt data at some point in time once we get some out-of-order mutations. So they're not commutative in this case. So an improved approach. Let's leverage the timestamp of the inbound mutation for how we do our inserts. So the RDBMS incarnation of this, insert into device, but adding a timestamp field so that we can always say, select back from the device metadata where timestamp is the largest. I'm oversimplifying the SQL here a little bit. It's kind of a heavy-handed approach. We're going to incur massive I/O on one side or the other, either on the read side when we try and read out the oldest value, or the newest value, excuse me, or in terms of creating indexes so that we can only read out one block that has the most recent value. The degenerate case here would be we have 30,000 updates, and we have to read 30,000 blocks on the database to figure out which one actually has the oldest value without an index, because we forego indexes to make sure that the right throughput is better. Neither approach is really an ideal situation. On the column store side, I did an illustration, infographic, yeah. So the first write comes in of timestamp 0 for the device, again, ponies, and the tag set would be a byte representation in the database here, but it's Beyonce. It's an array of tags, Beyonce. And then the Beyonce JZ update comes in, but again, we're out of order, right? So this is what it should be. This is actually logical update number 3 of 3. But then the second update comes in, but it smoothly inserts in between the two. So when we're reading from the column store in this case, we always read a slice of 1, which is the timestamp that is the highest value. This is effectively free in systems like Cassandra and HBase, that there is 1 or 50,000 beneath this. It doesn't really matter. Popping the top one off the stack generally works pretty seamlessly. So this is the sort of logical write-up of the schema. Again, the reads slice the top column. It's an easy incarnation for a log structure merge tree to actually do this. There's no transactions required in this case, right? It's a very small log footprint. Worst case scenario, it's a very small log footprint internally within a column data store, but we don't have to actually say lock the row key. We can just insert these things for free, and the column stores don't really care about that. That's the same of HBase or Cassandra. In both cases, we've, again, achieved idempotency, but we now actually have a rough approximation of commutativity, right? We can have these updates appear out of order, and if we read them, and the most recent version has actually come in, we're going to read the correct version. However, there's still some problems with this schema. The old versions are not automatically removed. So as we continue appending more and more and more versions, we now have larger and larger and larger rows, more and more blocks in the database. Depending on the storage engine, they're going to handle this differently. Arguably, we could use TTLs in this case to sort of alleviate this problem, but there's no good heuristic by which we set a TTL, right? Because we don't know when the next update is going to come in. So if we only ever receive one update and we put a TTL on that column and it's deleted, we've now lost data. And lastly, the problem that we describe in terms of I want to push to the device that has the tag of Beyonce, this approach makes secondary indexes very difficult to do, right? We have to look at the actual value of all these row keys to create secondary indexes, at least in a column store. So the winning approach, the Gongam style approach, is going to be a tag per column, where deletions are tombstoned. And this is effectively an oversimplification of the current implementation that we have in our tag system. So I tried really hard to provide a fair RDBMS analog to this, and I couldn't. And I'm sure there are people, I know there are people in the audience who would be better at this than me. So I'll try and update the slides after the Postgres people get mad at me for not providing good analog. On the column side, again, we have a key based on the device ID. But now we're actually taking the tag, and rather having the tag be an array in the value of the columns, we're making the tags first-class names in the columns. So that's either going to be a qualifier in HBase or a column name in Cassandra. And then the values are the timestamps that the mutations arrived. When a deletion happens, we effectively take the negative of the timestamp in the value But we leave a tombstone in place so that when additional when additional mutations come in, we can tell if we should drop those mutations or not. And lastly, the key critical component here is that the timestamp on each of those cells, so a cell means roughly the same thing in Cassandra and HBase, the timestamp on each of those cells is the timestamp of the mutation. What this means is that as a write comes in, if we try and alter one of those columns with an older timestamp, it'll effectively just be dropped. So we don't actually have to manually merge things. The data store does it for us. This gives us easy to rebuild secondary indexes because we can load an individual row and see what secondary indexes we should create. We never let the database in a HBase or a Cassandra world. We never let the database maintain secondary indexes for us for various reasons. But we can also do easy tag count manipulation, for example, so that we see when an index is, or when one of these values is being mutated, we increment a counter somewhere else. It's commutative, idempotent, so we've met those requirements, but it's also very fast. This is effectively what the column stores were designed to do. So this is what those updates look like. Effectively, the second update comes in, we have a timestamp of 1. The third update comes in, and now the Nickelback column has a timestamp of -2. When we read this row back out to see what tags the device has, we just simply drop anything that's negative in the value, or in the, that should actually be value, not timestamp on that label. So we read it, we drop anything that has a negative value, and then we know that we've got the most recent working set that we've seen from the device. So moving into sort of the operational consideration side of things and what we've learned in terms of operating Cassandra. Buffering. So a message when it reaches a broker is not immediately visible to a consumer. One of two conditions have to be met before a message will be handed off to a consumer from a broker. First, the log flush interval has to be reached. Interval is a bit of a misnomer here. What that really means is n number of messages have arrived at a particular topic, right? So if that value is set to 50, until you have 50 messages in that topic, none of them will be visible. Or alternatively, if log default flush interval ms has elapsed, then the in-memory buffer will be flushed out to disk, and effectively, at that point, the messages are visible. In either case, the messages are not visible to consumers until they've been flushed. So when they're in that intermediate buffer, they're not going to be delivered. The side effect of this is that if you're measuring latency through the system, you can get sort of false latency numbers that appear to be low throughput. If you're putting 20 messages into Kafka and you've got a consumer and either one of these thresholds hasn't kicked in, you're going to wait until the timeout happens, which could be 5 seconds, before any of those messages pop out the other side. So if you're measuring end-to-end latency between when a message is created and when it's processed, this can look artificially low at low throughput. When you get high throughput and you're hitting the first number over and over and over again, then the throughput looks excellent. But if you're testing this system and you want to say, what does it mean to put 1,000 messages through? It's probably not going to look very good. The system actually kicks in and performs much better in terms of throughput and latency at higher throughput volumes. And as sort of a side note, the smaller of these two values represents the potential for message loss. So if the window is 2 seconds and you're not meeting the count threshold effectively, and let's say the count threshold is 10,000 messages and the flush window is 2 seconds, and you only get 9,999 messages in there, whatever that buffer is, that's the theoretical number of messages you can lose. Again, higher throughput, better because you're flushing more often. The fetcher runnable. The fetcher runnable is effectively my nemesis in Kafka. At the end of the day, a consumer in Kafka spawns a number of fetcher runnable threads. Each one of these threads fans out and reads from brokers. The fetcher runnable feeds messages into internal queues that back the Kafka message stream object that we talked about before. All good. It's effectively a message pump. It's a pretty traditional architecture. But there's a critical caveat here, which is being a different thread that's feeding an intermediate queue that then the consumers consume from. The fetcher runnable has to remain healthy for consumers to see messages. So yeah, you can make out that code. That's a little bit of pseudocode in terms of what it looks like to actually consume a message. So you get a series of these message streams, and then in this case, it's submitting each stream to an executor, which is a different thread. And then the thread is iterating. If a fetcher runnable dies, this thread that is blocked on the for message data process message will stop. It will get no data, but it will still remain blocked on the queue. So you have to keep the fetcher runnables alive. As an illustration, you've got your obnoxious brokers up here screaming things, but they're kind of jerk faces, right? They don't really care if you ask them for things. If you don't ask them for data, they're just going to keep storing it. They're not sitting there waiting for you. They're not pushing things to you. Rather, the fetcher runnable has to go to the broker and ask for data and hand it off to these internal queues. that then other threads are consuming. But if the fetcher runnable goes away, nothing goes into the queue, and the downstream consumers get no messages. So given that the fetcher runnable is the lone source of data for one or more of these downstream stream constructs, when a fetcher runnable dies, the streams block. So what does that look like? Well, you get a nice, helpful log message that tells you that the fetcher runnable had a problem. But effectively, the fetcher runnable goes away, right? If you look at the Kafka code, the fetcher runnable will shut itself down at this point, but not inform the underlying queue that the consumers are waiting on. So now at this point, you have no mechanism for getting messages into the underlying queue. So what does that mean? That means that rate is king when it comes to monitoring Kafka. You absolutely positively must monitor your consumption rates along every use of Kafka, no matter how small. Kafka provides JMX beans that you can monitor. We don't really use those. We graph them, but we don't really do anything meaningful with that data. More importantly, we use Yammer metrics to monitor application consumption. We use the timer metrics, which give us effectively a distribution of latency in terms of every message that we consume. And if that rate goes down, then we have to alert. So you have to gather an initial baseline, effectively, to understand what a normal rate of consumption is and what normal latency looks like. And if that rate of consumption goes down, but latency is not changing, then you've got a problem and you need to alert on that. And you need to understand what the normal working band is and what a painful deviation from that is. Because there will be some ebb and flow. But outside of your tolerance band from that deviation of rate, you have to alert. There's no two ways about it. It helps to not overcommit consumers. So there's a slide later that talks about how to actually balance the number of consumers versus the number of partitions and brokers. But in terms of monitoring a rate, if we oversubscribe our consumers, so in other words, let's say we have a total of 64 partitions. If we have 128 worker threads, a lot of those are going to be idle, which makes it difficult to monitor the throughput of any one individual worker thread. You have to do an aggregate throughput across all of your consumers, which could be spanned across multiple hosts. It's much easier to have them undersubscribed so you don't have any idle consumers. The retention window. So effectively, when data is written into a segment file on a broker, every consumer group has an offset that logically applies to each of those segments files. That's what the consumers publish back in a Zookeeper. Individual consumers will move that offset as they consume a series of message within each partition effectively. So it's a combination of topic and partition. And the consumers are always constantly moving that forward. Segments are retained, each of those segment files are retained for a configured value. Like I said, we do about 7 days, log retention.hours. And then segments are deleted once they're outside of that retention window. So this looks effectively like so. We have segment 0 through segment 1, and each of them represents a certain number of viable offsets. If our working offset is at segment 0, and the retention window includes segment 0, everything's good. We move forward, we're processing messages, we move on to segment 1, the retention window slides forward, and segment 0 is dropped. No problem, everything looks good. But if we're not consuming fast, and the segment window outpaces us, and we're still operating on segment 1, when the window is now moving on to segment 2 and dropping segment 1, now the working offset doesn't have a segment with which to operate. In other words, we are consuming data slower than the producers are putting it in. And oftentimes, it takes a while to notice this if your retention window is 7 days, right? Because you can, the way this first manifested for us is a broker crash, or a consumer crashed. And we didn't know why, and we saw some messages in the logs that seemed to indicate that it had a problem talking to the broker, and we restarted it. At which point, we effectively went back to this, where the working set was the most recent one available, and we processed it for a day or two, but then the consumer crashed again. So when this happens, pretty much consider your world blown. Like, things are going to get really, really bad if you fall behind in the consumers. The best way to mitigate this is to monitor the consumers and the segment offsets, and make sure that they're progressing forward. And they should all be progressing forward in a relative lockstep, right? Each partition has an offset that a specific consumer group is operating within. And if one of those is standing still and everybody else is moving forward, there's a problem. So there's sort of a relative distance that should never be reached between the offsets in every segment. But again, looking for rates and monitoring consumption rates are usually going to catch this as well. Because effectively, if you lose a segment, now all of a sudden your rate is going to drop, right? A segment, consider, is one of a partition. So if you have 64 partitions and you're not consuming fast enough on one of them, you're going to reduce your throughput by 1/64th. So really, it's a function of the number of partitions you have, how severe it's going to be when you reach this condition. So I think this slide pretty much speaks for itself. I can't pass an opportunity to dig on Scala at a conference, sorry. But effectively, being a Java guy, I have a lot of problems with Kafka being written in Scala, not to mention one of which is this awesome Scala stack dump that when things fail in Scala and you get to read $anon, $init, parse, no, success, this is completely non-intuitive as a Java developer for me. So I won't linger on that too long. It's more just a jab at Scala. So brokers, hopefully this goes without saying at Surge, but monitoring IOPS and IO util, or IO utilization is critical on the broker hosts. Under no circumstances ever allow a broker to run out of disk space. Don't even let it get close. If that happens, your broker is probably not coming back, and your consumers are all going to be screwed downstream. Fetch size represents the amount of data that a broker will pull, or sorry, that a consumer will pull from a broker. Max message size is the largest amount of data that a producer should be able to write into the broker. Unfortunately, prior to Kafka 0.8, neither one of these was actually enforced. What that means is that these two bugs effectively caused our consumers to crash with a stack trace that looked like this. This is us trying to read a 145 megabyte segment and Kafka giving us 300K. And this was one line of code that was inverted in the Kafka source that the producer limit value was not honored. And so somebody actually put in 145 megabyte device update that when we tried to read it out, we couldn't get it back out. So this resulted in us monkey patching the Kafka code on the consumer side on the fly to be able to read a large value so that we could proceed forward. Not a situation you want to be in. This has actually been fixed, but this is what it looks like if you're not getting enough data from your broker as a consumer. Consumer tuning is an art. So on one hand, there's an inclination to overcommit. You want more threads than partitions so that if some consumers die, you'll pick up the work and you never run the risk of falling outside of the retention window. However, if you overcommit, effectively what you're going to achieve is idling. You will have consumer threads that have nothing to do because Kafka is not going to divvy up one-to-one every consumer thread for every partition. It's going to lump multiple partitions into one stream from multiple brokers, and you will have idle consumers. Often entire consumer processes, given the way that the balancing works. So overcommitting doesn't really buy you anything. Other than, in some cases, we've actually seen it have a propensity to cause excessive rebalancing. That can occur if you get, say, a decent-sized garbage collection on one consumer, and then all of a sudden Kafka moves a bunch of partitions over to another consumer. Same thing happens, and it's shifting constantly at many partitions. So generally, overcommitting, we found, is not a very productive use of the consumer's time. So that sort of leads to undercommitting. Well, OK, we'll have less. But again, you can run into problems in that the fetcher runnables are effectively serial for every partition that they're drawing from. So if I have 64 partitions, and I need to draw from all 64 of them as a fetcher runnable, that's done in serial. And if I'm consuming quicker than the fetcher runnable can go out and get data, I'm not going to have good throughput. Big garbage collections, if you have a small number of consumers, can also cause excessive rebalancing. Right? So if you are trying to limit the number of consumers so that you get a good distribution among consumers, effectively, if those consumers are working too hard, incurring too much garbage, and they have big, long GCs, they will lose their zookeeper lease, and somebody else will take over the lease for those consumed partitions. That is also not a good situation to be in. So we found roughly just right. The mix is about, for every 2 partitions, we want 1 consumer thread somewhere in the architecture. That really pivots very heavily based on the consumer workload. So if your consumer latency is very high, if it's crunching a lot of data and doing a very intense update, then having more threads is probably better at that point because your latency is going to be so high for each individual message you process, you won't keep up, and eventually, again, you'll underrun the retention window. This is my favorite operational learning of the entire slide deck. Incubator is going to incubate. So Kafka is an Apache Incubator project, right? That means it's very young. It means it's likely at this point been deployed in some large installations. I know LinkedIn uses it very heavily. I know we do. I know of a couple other people. But there's an awful lot of learning in production that's going on, right? It's an incubator. You should pretty well know what you're getting yourself into. It effectively hasn't lived through a long lineage of people being mean to it or using it in anger, right? It's just now getting to that stage where there's more uptake and people are finding all these edge case bugs. So this was a bug that we ran into a few months ago in June where the brokers were consistently ohming. Ohming meaning running out of memory if you're not a Java person. And you can see that the broker here is ohming with the size of a fairly large amount of data, right? What is that? 110 megabytes. So effectively, it's trying to allocate a 110 megabyte slab and failing. This happened out of the blue for us. It was not a problem. Then all of a sudden, immediately, all three of our brokers started sporadically incurring this problem. So the natural thing we did is, well, let's make the heap bigger, right? It's running out of memory, give it more memory. Surely it'll do better. Even though we've never had a problem with broker memory in the past, it was 2 in the morning at this point, so let's give it more memory. This literally continued on through the rest of the night with me personally restarting brokers every 5 minutes once we saw sort of the beginnings of this happening, and then another guy just reading through Kafka code frantically. By about 4:30 in the morning, one of our developers had the insight, I have no idea why this happened at 4:30 in the morning to do this. Anybody have an idea what this is going to print to the console? You get an UrbanAirship t-shirt if you know what this prints to the console. No guesses? It prints get. Our monitoring agent is an HTTP request. And our ops team had effectively pointed our monitoring agent at the service port on Kafka, and it was repeatedly hammering it with GET requests. Every time it did that, it never sent any subsequent data. All it sent was the GET, and then turned around and read on the socket waiting for the response. So the broker's saying, OK, you're going to send me something that is 110 megabytes in size. I'll allocate a slab and wait for you to send it, and then it would never send. So effectively, the broker was owned. When we figured out what was happening, we turned off the monitoring agent, we restarted the brokers, and everything was fine. But effectively, we were able to DOS our entire Kafka infrastructure by having an off-by-1 error in the monitoring agent setup. Right? This exact same thing happened with Cassandra. I know for a fact. This is what happens with young software. Right? This, I guarantee you, would not be a problem for something like Postgres. So with any incubator project, assume that it will be rough around the edges. This is a given. You need to know what you're getting yourself into. And assume that if you point your monitoring agent at the service port, things will break. Lastly, though, as a general best practice, make sure you measure the intended outcome of production changes. Again, hopefully that goes without saying, but it was if you consider that this was a monitoring change, right, we should have seen monitoring data show up somewhere, and it didn't occur to anybody to say, oh, there's no data after we cut over this monitoring agent. What's the problem? So a couple of acknowledgements. A lot of the commutative merge work was based on some work that Twitter did at FlockDB and Bobby Polito's Statebox. And the obligatory, we are hiring. We're looking for people across the board, so not just sort of this back-end systems infrastructure, but Django development as well. We need good operations people and infrastructure like the stuff that I talked about today. Please, if you watch this video, don't assume that my email is permission to try and sell me software via email. Questions? Yeah.
So you mentioned you had 3 different clusters, is that right?
Yes.
But is that sharded by like production testing or like this task versus that task?
Purpose.
Okay.
The clusters are all for specific purposes. So one is the operational data store, one is sort of the transactional data, right? Like a device is updating its metadata, and one is sort of the device delivery infrastructure cluster.
Did you go with bigger brokers, lots of little brokers, or what did you choose and why?
The brokers are all roughly the same size. They're what I would call sort of low-end, mid-range machines, right? So they do have a fair amount of memory. Kafka, because it's in-mapping all those files, if you give it a bunch of buffer cache to play with, is going to do very well. So they all have about 96 gig of RAM, and I think they're hex cores. But the drives aren't anything special. They're just, I think they're 15K SAS drives that are mirrored.
Okay, but how many like brokers per cluster?
Oh, 3. It's 3. Okay. We run, well, in some of the clusters, we run the Zookeeper and Kafka on the same boxes. In other clusters, the Kafka brokers use a shared Zookeeper, but the Zookeeper overhead usually is the more substantial of the 2 on the box.
Okay.
So you mentioned monitoring partition offsets. Is that something available through JMX, or are you monitoring Zookeeper directly? And then a follow-up, unrelated. Do you use Kafka with non-JVM producer consumers? And if so, could you comment on their efficiency?
OK, so to the first question, monitoring segment offsets, we do that via code that literally explicitly goes into Zookeeper and reads the offsets. And we effectively do a differential between all the offsets, and we have a tolerance window where if the differential is outside of that, then things are problematic. That's one view. We have a second view where we can literally look in a Zookeeper and the broker and say, how old is this offset? And if the age of that offset gets too far as well, then we start alerting on that. That is all so far custom in-house stuff. We should really contribute it back. Like there's no secret sauce to it. It's just understanding the Zookeeper layout predominantly and which sort of undocumented calls to make into the broker. There's really nothing difficult about it once you understand how the internals of Kafka work in the Zookeeper structure. And then the second question was non-JVM consumers, was that right? No, we don't have any non-JVM consumers. All of our consumers are in Java. I'm not aware of mechanisms for doing non-JVM consumers, but I will say that the wire protocol, if you can communicate with Zookeeper, which there's a C binding to do that, the Kafka wire protocol is very straightforward. So again, not being a fan of Scala, I've actually started working on a pure Java client that doesn't involve Scala, that is actually built on, say, like Netty, so it does in-IO pulls. So I mentioned earlier, right, the reads from each segment are serial. And so you're not actually optimizing the amount of data that you're pulling back down to the consumer. So the wire protocol wouldn't be difficult to implement in an alternate language, as long as you could live with the Zookeeper C bindings.
There's actually two different consumers. There's a simple, that would be like expert consumer, and that's just the wire protocol. And there's like a million different bindings for that of various quality. But the high-level consumer protocol that does all the clever rebalancing stuff we were talking about, that's Java only. And it's sort of unclear in the future how to generalize that.
Yeah, that's a good point. The rebalancing is fairly intricate, so you'd have to end up rewriting that on the consumer side.
I was just kind of curious how much Scala you guys use in production in any other projects.
So we've evaluated using Kestrel, to have sort of both of our point-to-point and pub/sub on sort of a similar type platform. But other than that, nothing. Everything else is non-Scala. This is the only Scala production piece of our stack, I think. If there are others, I'm not aware of them. Yeah. Okay, thanks.